Welcome to Brain Vision.
Okay, so for this question, we can apply the energy balance equation here, which is E dot N equal to E dot R. If we expand it, we have M dot H1 is equal to M dot H2. As you can tell, M dot can be cancelled out. So this will give us H1 is equal to H2, which means that the enthalpy through the process is constant. Okay? And then if we take a look at table A12 at the back of the book, which is the saturated refrigerants 134a pressure table. So at 120 psia, you'll find that the corresponding enthalpy is 41.787 British thermal units per pound mass, which means that H2 is also equal to such value, since H1 and H2 is equal to each other. And then you'll find that the corresponding internal energy is 41.485 British thermal units per pound mass. And the saturated temperature, which is the corresponding temperature for the inlet temperature in this case, T1, is equal to 90.49 degrees Fahrenheit. Now let's go to the different pressure here, which is the pressure at the axis. Okay, so at 20 psia, we can find that the saturated liquid enthalpy, which is HF2 here, is given as 11.445 British thermal units per pound mass, and the saturated vapor enthalpy, which is Hg2 here, is given as 102.73 British thermal units per pound mass. And the saturated liquid internal energy, which is UF2 here, is given as 11.401 British thermal units per pound mass. And the saturated vapor internal energy, UG2, which is given as 94.3 British thermal units per pound mass. And the corresponding temperature is negative 2.43 degrees Fahrenheit. So now we can determine the temperature change, which is delta T here. And delta T can be equal to T2 minus T1, which will eventually give us delta T is about negative 92.92 degrees Fahrenheit. In order to determine the change of internal energies in this case, we need to determine the quality at outlet first, which is X here. So X can be equal to H2 minus HF2 over Hg2 minus HF2. If we plug in the values, eventually we'll have the quality at the outlets is equal to 0.3324. So now we can use the quality outlets, which X here, to determine the internal energy at the axis, okay, which is U2 here. So U2 can be equal to UF2 plus X times UG2 minus UF2, which eventually will give us U2 is equal to 38.9566 British thermal units per pound mass. So now we can determine the change of the internal energy through the process, which can be equal to U2 minus U1, which will eventually give us the changing internal energy is about negative 2.5284 British thermal units per pound mass. Okay, and these are the answers for this question.